Hello, everyone. I'm going to work through a couple of stoichiometry problems with you. Now, these are going to be what we would call limiting reactant problems in stoichiometry. Okay. Now, to tell you the truth, from day one that we've been doing stoichiometry problems, we've always dealt with the limiting reactant. But it was always easy to know which reactant was limiting because we always had one reactant in excess. I mean, in other words, if you have a room full of oxygen and you light a match, you know that the reaction is going to stop when you run out of the match, right? You're not going to suck all of the oxygen out of the room while the match is burning. So, if you have excess oxygen in one match, well, you know that your match is the limiting reactant. Well, now it's not going to be as obvious, okay? Now we're going to be given a couple of uh, quantities of reactants, and we're going to have to decide which one is the limiting reactant. Because the amount of stuff that we can make in a reaction is limited by the limiting reactant. Okay, so let's start with this first problem. Now, the first thing that you've probably seen is this is kind of weird looking. Um, there's this crazy symbol here that shouldn't be that at all. It should just be an arrow. So um, this is our balanced chemical equation. And we always use a BCA table. So why don't I just draw a BCA table right away? We haven't even looked at the problem yet, but let's just go. So that's before and change and after. All right. So in this problem, we're going to combine 3 moles of hydrogen. I'm just going to put a 3 there, and 2 moles of nitrogen, and which is going to be the limiting reactant, and how many moles of ammonia can we produce. In the before part, of course, we haven't made anything yet, so the amount of ammonia is 0. Okay, so we are given an amount of hydrogen and nitrogen, and we have to decide which of these are we going to run out of. Okay, now I think in order to get started with this, I want to show you something that I know is not going to work. Okay, and then we'll start over again, and then we'll solve the problem. I want to show you what doesn't work as well as what does work. All right, um, because I want you to get the idea that if you try something and it doesn't work out, just start over again and try it again. No big deal. All right. So here, let's try this. I'm going to do this in a different color. Okay, so let's try this. I'm going to use up, let's see if nitrogen is our limiting reactant. If I use up all the nitrogen, then I would end up with 0. Now, take a look at the mole ratio. For every 1 nitrogen, I need 3 hydrogens. In other words, if I'm given 2 nitrogens, I'm going to need 6 hydrogens. And that is impossible. There's no way that I can take 6 hydrogens out of the 3 that I'm starting with. That's impossible. I can't end up with minus 3 hydrogens. So, like I said before, we're going to start over again. All right, so I know that the limiting reactant cannot be nitrogen. It must be hydrogen. So what if I used up all 3 hydrogens? Okay, if I use up those 3 hydrogens, I'm going to use up 1 nitrogen, right? It's a 3-to-1 ratio when we look at the coefficients. We'll end up with 1 mole in excess. Okay, we're going to have 1 extra mole laying around. This is our limiting reactant, the hydrogen. We run out of the hydrogen. Okay, so the next question is, how much ammonia can I make? Well, why don't we take the easy route and say, I know that for every 1 nitrogen, I can make 2 ammonia. And actually, I did use 1 nitrogen, so I'm going to make 2 ammonia. And that is what I'm left with. Or that's how much I made. I think it's also maybe important to get into the habit now of converting moles to mass. Okay? I know that every 1 mole of ammonia is 17 grams. I hope you can see why that is by now. But 2 moles is going to be twice that, right? So that's going to be 34 grams in the end. It's not being asked for in this problem, but this is something that we're going to be doing over and over again. So why not get in the habit of it? Let's try another problem. Okay, well, why not go ahead with number 2? So again, I have no idea why that symbol is there because that should be an arrow. I am just going to start with a BCA table, just like we always do. And here we go, BCA. Given 20 moles of hydrogen, and I'm given 11 moles of oxygen. So I want to know what is the limiting reactant, and then I want to know how many moles of water I can produce. All right, before the reaction starts, we've not made any water. Okay, so like I did before, I'm going to start with a scenario that I think is not going to work, just so to show you why this approach doesn't work and that we're going to try another approach. Okay, so let's say we were to call oxygen the limiting reactant. And let's say I used up all that oxygen. If that was the case, then I would need 22 moles of hydrogen, right? The mole ratio is 1 to 2. For every 1 oxygen, I need 2 hydrogen. If I used up 11 oxygen, I would use up 22 hydrogen. That's impossible. I can't possibly take 22 out of 20. So we'll scrap that idea and let's try hydrogen as the limiting reactant. Okay? And by the way, you're always going to use up one of these reactants. Okay? You're always using up all of one of the reactants. All right, so I'm using up all of the hydrogen. And if I was to use up all of that hydrogen, I would use 10 oxygen because that's a 2-to-1 ratio, and I would end up with 1 mole excess in the end. Okay, so I'm going to end up with extra oxygen, and hydrogen is my limiting reactant. All right, how much water can I make? Well, this is easy. For every 2 hydrogen, I can make 2 waters. So I used 20 hydrogen, so I'm going to make 20 waters. And that is the answer. So I answered that question, how many moles of water can be produced? Why not just take it to the next step and say, well, how many grams would that be? I know that 1 mole of water is 18 grams. Okay, so 20 moles is going to be 20 times 18 grams, and that is going to be 360 grams of water. Again, I know it wasn't asked for, but I just wanted to get into the habit of converting to mass, and if given mass, converting to moles, okay? There's nothing different there. There's nothing new. In fact, we were doing mole calculations early in the semester, okay? So this is old stuff now. All right, let's try a different problem.